All right, we're kind of funneling in. I think we're going to start soft, and then we'll get into the more like head spinny stuff at the end. Brent doesn't know what we're doing. So I did give people a warning as to what we were talking about today. So be prepared, Brent. So today we're going to start off with counting. And I'm actually recording. You can tell I still have this stupid lingering cold thing, but I'm allergic to cats, and I've had over the past couple months, 9 cats or something in our house, which has perpetuated so many things. So we're finally out, and I spent the last couple days like clearing out all the cat hair and stuff, and I think it's just getting to me. All right. So today we are starting on a fun topic, and I love it so much that I just couldn't even bring myself to PowerPoint because I wanted the freedom to go any direction I wanted. I love counting. So counting is a fun thing. You've done it since you were 5 years old. And it's really simple, isn't it? Does anybody want a demo? Brent, you know how to count, don't you?
I feel this might be a trick question coming up.
It could be. Counting is I even though we can't hear you, Brent, I'm pretty sure he knew 1, 2, 3, 4, 5. He's close to graduating, right? So we have faith he can count. Except, sometimes counting is a bit tricky. So, in fact, we're going to start off really easy. So we're going to start by saying, well, how do we count things in a set? Good morning, Adam. I see your message. We're having a delay here. If I have a set and I put 5 marbles in it, how many items do I have in that set? I can think of a set containing 1, 2, 3, 4, and 5. How many items do I have in that actual set that I've exhaustively listed for you? You might as well answer now. It gets more fun later. Yeah. You don't even need the question mark, Adam. Even pre-coffee, I'm pretty sure we're happy to say that I've got 5 marbles in here, and I've got 5 digits in my set on the right. And the way that you do that, now it is early, fair enough. Exactly. Don't be scared. Most of these things are very straightforward. But the reason that you can confidently say that there are 5 elements are because counting is a basic principle where we map the natural numbers, those numbers that I believe Brent was spouting off for us, 1, 2, 3, 4, 5. This is the natural numbers are written like this, or what we've been using is z greater than 0. Okay? But what we do is we take those natural numbers, and as I joked about earlier, my favorite story of my daughter was that I said, well, what's the largest number? And she said 576. And I said, well, what about 577? She said, yeah, I was close. They don't stop, right? And we know that. And so they're an infinite number of natural numbers. So I can keep counting forever. But what we do without thinking about it, because we've done this since kindergarten, which is why counting feels that it should be very easy. And for today, we are going to stay in the easy realm, okay? What we do without thinking about it is we take those natural numbers and we map them to the objects in that set, right? So if I say, tell me how many fingers I have on my hand, you know it's 5 because that's a fact that you've come to grips with. But really what we do is we are mapping 1 to this finger, 2, 3, 4, and 5. And because sets have no order, and when I ask the number of fingers on my hand, it doesn't matter if you counted in the other direction or you counted this 1, 2, 3, 4, make sure I do that in the right order, 5. It doesn't matter. We're still going to get to the cardinality of that set is 5. And so when earlier in the semester, we talked about sets and we talked about set cardinality. So if this is my set A, which is the numbers contains 1, 2, 3, 4, and 5, easy to see there are 5 elements. But what I'm asking for when I'm saying I want you to count the elements of the set, I'm asking for that cardinality. So the cardinality of A in this example is 5. And the reason for that is we're mapping. I've got the objects in my set. Let's say I have a different set. Set S contains the lowercase a, lowercase b, lowercase c, g, and f. Okay, and you might say, well, why not D and E? Then I know E is the 5th letter. But if I just had a hodgepodge of letters, what you would have to do is figure out what is the size of my set S. And the way that you do that is you assign each of these a number. So you have this mapping from the natural numbers to the elements in that set. Okay, and I know this might sound trivial, but that is how we define counting of a number of objects. We're mapping those natural numbers to the elements in the set. Okay, so what if I have 2 sets? I've got a set A, and it has 7 objects, and I've got a set B, and it has 5 objects. What if I want the union of those sets? What does that look like? Okay, and today, for better or worse, this topic needs a lot of thinking, and I always want people to be part of this. So I really would like answers. If you can and feel comfortable, please feel free to mic up, raise your hand, but throw an answer at this. What does this look like? Oh, there we go. So I'm asking, what is this? The set or the order. I want the cardinality of that set. Okay, so I see an example for 12, 13, got a few things going on. Anybody unclear now what the answer is? I see a question mark, Abhishek. I see 7. No more than 12. All of these answers, no more than 12. Schwan, I like this. Okay, and now I'm going to have you think about it for a second. And I'm going to say, oh, it depends. You would have to know what is in each set. Well said, Brent. And I know some of those might have just been off by 1 errors, and that's okay. So how do we know what it could be? Well, let's go back to one of our favorite things, which is a Venn diagram. So first I had a set A, and in it were 7 items. Okay, so I'm going to put this, remember we have A is 7. And then I've got a set B, and B was 5. So I'm going to give you a couple examples. Somebody was right. They said it could be 12, and they put a question mark. Now, I think 12 question mark is a valid answer. If I put 7 items in A and 5 items over here in B, I don't know what they are. And if my Venn diagram looks like this, then if I look at everything in both of them, it's all of those things. So in this example, A union B is equal to 12. But what if my Venn diagram looks like this, and I have some item in the middle? I still have an A and a B. A is still equal to 7, B is still equal to 5, has cardinality 5. Now, what is the size of that union? Yeah, exactly. So now we can take even that question mark away. Now I've got six items that are in A that are not in B. And I've got 4 items over here in B that are not in A, And then I've got this one that they share. And the thing about them sharing that one is I'm essentially counting it twice if I say that there are 12, right? So this one is in both. Oh, it's very sensitive today. And so in this case, it's 11. Yeah, we only want to count that middle one once. Okay, fair enough. Now what if I have a larger overlap and I've got 3 in the middle? What's A union B? Remember, this has 7 and this one has 5. I think we're getting this. Yeah, so how many are in A that are not in B? There should be 4 over here. And then I've got an extra 2 hanging out in this space. So if I count that up, I've got 6 plus 3 or 9. So now, yeah. If I say I've got A equals 7, B equals 5, what is the size of A union B? Pardon me. And feel free to use your mic if it's more than you want to type.
Angela, can you hear me now?
I can.
The cardinality of A minus or plus the cardinality of B in brackets minus the subset of A and B.
Okay. I think so. I'm going to write this down, and you tell me when I have it right. So, A union B is the cardinality of A. Say it again. Plus the cardinality of B.
Of B.
Minus.
And like all of that in brackets, technically. Or I guess it doesn't matter. Minus the subset of A and B.
Okay, I think we're looking for a different term, but I think you're right. You're onto something here. So I think what you're trying to say is you want this piece, right? You want to take this away.
Yeah.
Yeah, which is great. So help him out. What is the term for that? This is a way going back in time now, back to sets. And this is like early weeks. Yeah, the intersection. And the way that we write that is A intersect B. Yeah, well done. Adam, that was perfect. So, like we're going back to week 2 for this type of stuff. So that's exactly what you're looking for. And so the reason for that, if you think about the Venn diagram, and it doesn't matter what is in that size, you've got the elements in here that you're counting, right? That's the size of A. And then you've got all the elements in B that you're counting. But look at this spot here. This is over-counted. We've counted it twice. And so what we're doing was we're saying, if there's anything in there, remove it. Now, does that always work? What if there's no intersection? Like, what if my Venn diagram looks like this? Can I still use this formula?
Then your intersection would be 0. So it's
yeah, exactly. It's all good because in this case, down here, A intersect B is equal to 0. And so the whole thing in that case was what you first came up with, which was we can just add up what's in A with all the elements in B and we're good because the intersection is 0. So if the intersection is empty, if A intersect B is equal to the empty set, then we can go ahead and say we just add up all the elements. But if there's anything in the middle, then we're going to be double counting. And so we need to remove that. Okay. So let's think of an example that you can apply that to. Okay. So let's let A, and then we're going to talk about, well, why does this matter? because ultimately what we're trying to do is apply this then to programs that we're running. And there are times that you want to know, well, how many times am I going to loop through something? If I want to take an estimate on the time that something's going to run, then you need to know how many times it's going to go through each iteration. And so oftentimes what you're doing is, you don't think of it necessarily. You haven't until now thought of the elements that you're looping through as members of a set. But they are, right? We can define those abstractly as the set of all things, starting from, so oftentimes we'll have a starting point. We'll say, okay, we're going to go from int I equals 0 to I less than 10, and we're going to go up by 1 each time. Okay, so we're going to go up, we're going to add 1 each time we go through the loop. And what that means is we're going to start with 0, we're going to go through 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And that right there, that forms a set. Those are the set of numbers that when you're looping through your programs, those are the numbers that you're going to encounter. So in this case, it's fairly straightforward, right? We're going from 0 to 9, but there are times that this calculation is more complex. There are times that this is not a number, but there's a calculation involved in that. And so you could define that as an abstract set, and then you can find the cardinality of that set based on counting techniques. Okay, so you might not have been thinking about, well, how does this map to computer science? But these are some of the ways that it does. And so I'll try as I can. Oops, that's not what I meant to do. Still not what I meant to do. There we go. And so can you think of any other times that you're working technically with sets in the programming that you're doing in 1105 and 1110? Mathematical sets, not sets in the sense of... Yeah, so in while loops, arrays, well spotted, Luke. Yeah, how about, is there anything even more simple than this? A fairly basic data structure. Yeah, linked lists are another one, Anik. I suppose you guys you're all probably right around that. Databases are set, and a string. Trent, that was the one I was looking for. In terms of really simple data structures, even strings, they're containing in that case, more of a sequence, but it's still a set of characters that happen to have an order, and so they form a sequence. Okay, so all of these things are things that we can then relate back to sets in the sense of counting them. So even things that are sequences, we can think of them in their base level and just say, okay, as a collection of items, how many are there? All right, so for instance, if I asked you then, since we just were talking about that, if I said, and I think I'm about right, in discrete math, our set D has 94 students. And I'm not exactly sure the size, but we'll say CSCI 1105 has about 110 students. How many students are there that are taking discrete math or computer science this term? CSCI 1105 this term. So this is, D is the set of discrete math students. And C is a set of 1105. Oops. If I said, how many are there that are taking either D or C? Possibly 94, someone says. Maybe 110 to 204. We've got a range. Actually, can we put a range on it? That's a great piece. Can it be as low as 94? Can it be as high as 110? And I think what's tripping people here is D or C. And then I say, okay, well, what about if they're taking both D and C? How many people are taking both discrete math and 1105? So already we have some questioning, but I'm curious because we know how to count, right? We know how to map numbers to things. So why is it hard? And you're not wrong to be confused right now. Why is it hard to give me an exact answer for this with this information?
Would that be because we don't know where the intersection would be? Or who's in the intersection?
Exactly. And so if we had a list of all the students, like if I said raise your hand if you're in both discrete, if you're in this class and you're in 1105 and we were all here, then we would know immediately what that answer was, right? Because if I said if you're taking one or the other, well, what would that look like? If I gave you that extra piece of information, and I don't know it, but if I said the number of students that are in the intersection is 25. Now what's the answer to D or C? Well, first of all, what is D or C? What does that look like mathematically? What am I asking for? What does that or translate to? Yes, union. So in this case, I want D union C. And what does that look like when I say that there's a 25-person overlap? Looks like duck. Now I know that I've got a set of 94 students that are in discrete. I've got a set of 110 students. So there's 94. This is D. There's 94 over here. There are a set of 110 students over here, and there are 25 in the middle. So C plus D minus D and C. Yeah, I know what you mean. The intersection. And so that intersection, so it's that 94 plus 110 minus 25. So this 94 plus 110 minus 25, whatever that is. I don't even care what the actual answer is. So if I look for D and C, those students that are in both discrete and 1105, what does that look like? With all the same information provided. Yeah. So is there a number we can place on that one? This one I can do. We were given it. Exactly. Thanks, Daniel, Adam, Simran, Juan. Everybody's got the answers now. Okay. So now we're getting somewhere. And so how do we then map that to things like, okay, let me work on another example. So, what if I said, I want, and this is more about figuring out what sets you're even interested in. Okay, so sometimes counting is just figuring out what would I do with this. So if I said, I want the number of passwords available, and I'm going to use my kids as the example, that are 4 digits. So this is like the classic cell phone, iPad password. Okay. And I have kids that are teenagers right now, 13 and 15. Okay. If I pick up any of their friends' devices, and I have, I'm terrible, but I taught cryptography. And so I feel strongly that kids need to learn about passwords early on. And so I will take a random photo with their phone. I know all of their passwords. every kid that age, their password is the year they were born. Every single one of them. And I don't know why, but just if you ever have kids, don't let them use their year of birth. I'm sure it was set when they were very young and no one cared and they just kept it forever. But everyone uses the year of their birth. And so if you have 4 digits, but because of their age group, I say, you know what, the first bet, that's true. I have crazy passwords, but in fact, I should share with you all, there was a list just put out yesterday of the most common passwords, and some of the ones that are on there are just hilarious, like password 1, you know, and 1, 2, 3, 4, 5, 6 is another common one. Yes. Also, why this one? Okay, I'm going to be distracted. I'm really excited about that list because they're just hilarious. And I will send a link, but at any rate, they're pretty bad. So what if I said you can have anything you want, but you cannot have anything of this form? I don't want to see something that looks like a birth year for this group. So you can't have anything that starts off like this. In fact, maybe I'll even, to make it easier for you, we'll say it can't start with 200. What does that look like? How do I count the number of passwords in this case? And this is easy because we're starting from numbers. So basically we're just removing things. But what does that look like? If I want to say, well, what's the set of valid passwords, the size of the set of valid passwords? That's still then equal to what? What does that even look like? Now sometimes we can think about, well, what do I need to remove from the set? So sometimes what you want to count is those that you want the size of the whole set and those that you need to get rid of. So what does that look like in this simple example where I've got, we'll make it easy. It can't start with 20. And in fact, we'll cover other cases. So it cannot start with 20. I don't want to see anything that looks like a birth year. What's the whole set? How many possible passwords are there? 4-digit passwords. Okay, I see some answers coming in. Yeah, so what's the size of the whole set? It can run from 000, don't forget that one, all the way up to 9999. So I've seen a few 10,000 and I've seen a few 999s. Here's what I would say. This off by 1 error, it's a real thing. This right here, that's our 999. Okay? Add this guy in, and we've got our 10,000. Those off by 1 errors are going to slowly eat at us, right? Forgetting the 000 option is a big thing. And then somewhere in the middle, so this is my set of like possible passwords. It's the size of that set is 10,000. And then somewhere in the middle are my invalid passwords. And those are the 2000, 2001, all the way down to 20, and apparently I'm really getting rid of everything, to 2099. So how many of those are invalid? I think we got 10 squared from Arash has the answer there. Yeah, so and Trent as well. Yeah, so we only have 100 invalid passwords. And so what I'm actually asking for is the size of the possible minus all of those invalid. And this is really back to sets. So when we ask about counting, sometimes what we're doing is we're saying, look at the collection. How would you get to the set that of interest? And that is start from the whole set and remove those pieces that are not allowed to be there in this example. Okay, so that was our 10,000 minus 100. Perfect. Okay. We're going to go through more examples like this in the future. But actually, I'm trying to think if I want to take you in a new direction or if I want to just have a bunch of time to play with some things. Okay. We're going to have a bit of fun. It's Friday. All right. I'm going to give you a number. Abhishek, welcome to my hotel. My hotel is called Hotel Infinity. Oh no. Oh, who said, oh no? I can't see. I just moved so I can see your list. I'm going to be checking up on, I think it's Adam. No, Daniel. Hotel Trivago. We're going to go, Adam, have you seen this? And so now you're terrified, or you've seen this and is it another rigged game? It possibly is. It's okay. I promise. Okay. So we have really big keys in our hotel because we've got a really big hotel. And so I have to have many different combinations to let you into your room. Don't freak out. It's a great hotel. We have beautiful spaces. Okay. And so I'm going to go through and I'm going to assign you to a room. Abhishek, I welcome you. I'm in room 1 because I run the hotel. I need to be there. Abhishek, you'll take room 2. Adam, you're in room 312. Alexander, we'll put you in 314. Anna, room 315. Anik, room 316. Arash, keep your number, 317. Ardavan, you're going to go into 17. I know that one's still free. Axel, 318. Bertram, 319. And I think what I'll do from here, because we have a long list, is we'll stop. But I know I happen to have enough to cause a few bits of trouble. The rest of you that don't have rooms, don't worry. You've got a room. I've got a bit of a cold. Burnley, of course you can. 18. Make sure I'm not doubling up. One of the rules of our hotel is that we only allow 1 guest per room. It's a large hotel. However, they're very small rooms. So there's only room for 1, unfortunately. If anybody else would really like a room, I can give you one. I know, small rooms. I am sorry. It's a bit like the Philadelphia Four Seasons, unfortunately. Yes, the one that Trump went to, not the other one. Prison Infinity is a fair assessment. Okay, so I've got these rooms, and I know I have a few people allocated, but don't worry. It's going to take us some time. Our great concierge, Brent, will be giving you keys to your rooms. And I'll just let you know how it's organized so that you can find your room. It's a long hallway, so just keep walking. But I'm in room 1, and you can find me right here. Tip the bellman. Yes, please tip our bellman. And the rooms are in order. And in fact, we have every natural number as one of our rooms. Fair, right? So if you can conceive of a number with a certain number of digits from 0 to 9, we have it. So we do have the room 13,789,456,211. And in fact, who was it? I think I didn't get, Juan, you did not get a room. Is that correct? That's your room. We'll put you in there. That's your room. So we do have many a room, and it just would take so long for you to get there. So yeah, we had to keep the rooms a bit small, but do not worry. We can do it. Okay, so I believe everybody's gotten a room now. Is that right? Brent, could you confirm that everybody has been assigned a room? Is there anyone missing a room? Assigned.
That's a tricky thing to figure out, I think.
I mean, no. I mean, theoretically, it's just a game. It's okay.
Yeah, okay.
you have, quote, assigned everyone a room. Is that right? Wink, wink.
Yes, everybody's got.
Oh, excellent. Okay. Brent, but we didn't give you a room for the night.
That's okay. I can sleep in the closet. It's fine.
Well, that has been known to happen at this hotel. Brent, I have a real issue here because, as it turns out, all of our students have gotten a room, but we had an incredible amount of guests arrive after them. So while you were helping them with their bags, hopefully getting an infinite number of tips in the process, we had a huge busload of people. It was an infinite bus run by our company, Infinity Buses, and all of our rooms are full. So first of all, the question is, and I'm sure you played with this at some point in time, but how many people do I have in my hotel if all of my rooms are full? Somebody requested control. That was fun. Can you still see this?
Yeah.
Okay,
that's good.
Cool. Okay, so I think I see, I need to go off of the names of people. So I see that people are saying this is infinity. Absolutely. Yeah. Well done. Okay. So the big point of this type of counting, and actually my daughter is in grade 3, and so she's just been playing with infinity, and it really bothers her because people have said that infinity is a number. So she's the symbol for infinity. I'm sure you've seen it. Oops, I've got an eraser going. Looks like this, right? Infinity is a size, but it's not one of our counting numbers. So our natural numbers 1, 2, 3, 4, 5. Those are by nature. This is defined to be the size of the set of those natural numbers. So when we talk about infinity, what you're saying is something has the same size as the set of natural numbers. Okay? And so that is our definition of infinity, and that's what we map things to. And so if we want to show that something is infinite, then what we're doing is we're showing that I can map every natural number to an element in that set forever. So there's some mapping that will get us there. Okay? And because of the way that I set up my hotel, where I have rooms that start from 1, 2, 3, 4, 5, 6, and so on, that means that my construction is a mapping, right? Room 1 maps to the natural number room 1, room 2 maps to the natural number 2, etc. Okay. Which is what I stated was how we count. And we will continue to do that. So when we're mapping sets and we want to show that 2 sets are of equal size, even if they're infinite, the way that we show that they're the same size is we find a mapping from one element to in set A to another element in set B. Okay, so we're going to come back to that in simple ways later, but unfortunately, despite the fact that our hotel is full, Brent does need a room. We don't allow our staff to sleep in closets. So where should we put him? I don't let students sleep in closets either. So as many of you would be willing to give up your room for Mr. Brent, we can't do that. At the very far end. Keep walking, Brent. I like it. Okay, so all sorts of great answers. So the answers that have been provided so far, Brent, are infinity plus 1. So hold on 1 second. I need a helper. So, as I mentioned, she feels strongly about infinity. And, Christian's put you in the bathtub, Brent. Come here, honey.
I saw that. Thanks,
yes.
Christian.
I don't know if that's... So.
Hello.
So, we're trying to find a place for Brent. Now, Brent is going to stay at our hotel, and we have a bunch of rooms that start from 1, 2, 3, 4, 5. Now, the question is, can we put him in the room? We want to assign him a room number. Can we put him in infinity plus 1? Is that a number?
No.
Why not?
Because infinity is not a number.
Infinity is not a number? Okay, so this one feels very strongly about this and has corrected her teacher a few times. But infinity is not a number. Well, it's hard to argue with his face. How do Adam, I like the workaround. The size, the cardinality of the natural numbers plus 1. The problem is, with my infinity hotel, I must give a key. And the keys that I have only have natural numbers on them. So the question I have for you is the cardinality of the natural numbers plus 1, is that a natural number? Do you know? She says, Well, you would think, except, how could it be? Now I'm going to ask you a question, and this is the head spin of infinity. If the cardinality, what we're saying is that the cardinality of the natural numbers plus 1 is in the natural numbers. Is that what we're saying? That's what we're asking. We're trying to say, is this possible? If it were, wouldn't that increase that cardinality by 1? So wouldn't that be this sort of repeating problem that we've created? So we're creating a form of recursion that's a little messed up. Yes? Okay. So what if we can't do that? And in fact, we can't. Yeah, it's an infinite recursion that you just created. Okay, and while I love playing with infinite recursion and recursion in general, I'm going to tell you right now, my daughter's conviction that this is not a natural number, she's right. Because infinity is not a natural number. So the cardinality of the set of natural numbers was talked about thousands of years ago, right? This is something that has troubled mathematicians for a very long time. But infinity is a defined item. It is the set of all natural numbers, and that itself is not a natural number. That is a transfinite number. Okay, so that's a fun big word. Whoops, that needs a pen. So infinity is transfinite. And transfinite means it's beyond what is countable. It's beyond the finite. Things that are countable are finite. This is beyond that. This is called beyond finite. So she does have the help of having played with this before. Also, she, like I, has had nightmares about infinity, which is so funny. Just from the sense of like never ending. And I suppose when you were doing your recursion projects, you might have as well. And I apologize for that. So this is beyond the countable numbers. Uh-oh. What that means for us is I now have a problem. Because all of my rooms are full. This infinity plus 1, which is a very valid suggestion, doesn't work. Where do I put Brent? Infinite nightmares. That's true. I'd rather have one infinity nightmare than an infinite number of nightmares. Well done, Stephen. Okay, so I have a suggestion. Hopefully you know your room numbers. Why don't we give him my room? Brent, you're graduating soon. I'll give you my room.
Why, thank you.
But I need to go somewhere now. So I'm going to take room 2. I think that one's free, isn't it? Isn't room 2 free?
I don't think so.
Oh, I said my whole hotel was full. And in fact, I think we know who's in room 2. I think Abhishek is in room 2. Abhishek, are you in room 2? Well, that's okay. Abhishek, you can take room 3. Can you take room 3? No problem. There's someone there. Just move them. Keep moving them. Sure. Yeah, no problem. Okay. 16, you're going to take room 17. Is there someone in room 17 here? I think yes. Keep switching. Yeah, 17, you'll take 18. I think somebody else from our class is in room 18. You just move them down. And so what I'm going to ask all of you to do, so I do have an infinite loudspeaker in my hotel. It also looks like an Apple Pencil. So in my infinite loudspeaker, I'm going to say to all of our guests, please pack your bags, move one room down. So if you're in room 17, move to 18, 2 million, move to 2,000,001, etc. Is this a problem? So I'm exactly, Adam. So we're taking, if you're in room K, please move to room K +1. Now the question is, can we do that? Our hotel is full. Can we accomplish this? We can. We have infinite Ks. Exactly. So everybody's going to move over by 1. And that's going to essentially free up this space. And Brent now gets room 1, his well-deserved space. But what does that mean? Yeah, why is that different, Burnley? This is the head spin of this game. Infinity is not a natural number. Infinity +1 is not a natural number. But K is a natural number, and I can find a mapping where I move K to K +1, which we just did. Okay, so that is our move. If this is a natural number, so is this. Right? I can always add 1. So each of the rooms is a natural number. I haven't messed with anything. But what have we just shown? That's a little weird because essentially I'm going to say I started with infinity people in my hotel. That was the number of people in my hotel. But I just added 1. Right? I did move to infinity +1. Correct? And while this is not a natural number, what does it have the same size of? I just took an infinite number of people in an infinite number of rooms, and I added a person to that. These were my people, and I fit them in a set that we know is just the size of all the natural numbers. I have a hotel that maps to each of the natural numbers. So I know that I fit infinity +1 people into the cardinality of the natural numbers. They fit in there. Yeah. So it's added to the set, but it doesn't change the cardinality because it's infinite. And so the cardinality of this set that has infinity +1 items in it, the people, it's still infinity. And so infinity +1 is infinity, which is a little messed up. And this is where, this is called, for a fancy word for the day, which is, I'm more interested in the mapping and how we can move things around and still fit things. But just so that you can feel like you have something to talk about that other people won't understand, what you just did is transfinite arithmetic. Okay, so for a little more transfinite arithmetic for a fun Friday, I have a bigger problem. So we've got Brent in here. And this is about thinking about how do we solve these weird problems. And I'll come to the end, I'll talk about why on earth this mapping process matters. Okay, so now I've got, oh, Stephen, yeah, these are big. Okay, Burnley, good questions. I didn't see these. Sorry, these are really important questions. So Burnley, your question, and I think Stephen's at the same time, is is it still bigger than just infinity? So is the question, how do I compare like infinity plus 1? Is that bigger than infinity? Is that the question? Actually, and we will not get into it here, Stephen, but yes, there are things that are bigger than infinity. There are levels of infinity that we won't touch on here because I think this is enough of a bit of a head spin. Yeah, so if we can reach in, we're not actually. So the question here is just with addition. If I have infinity, is it bigger than infinity? Infinity plus 1, is it bigger than infinity? Yes, Daniel. I can post links as well. There's some really great ones about those, about transfinite numbers. Yeah, how to count past infinity. The reality is that these are no different in size. And so a set containing infinity plus 1 elements is the same as a set containing just infinity. It's pretty messed up. And in fact, one of the things that you don't realize is that we use this all the time. Okay, so for instance, and here's how we're going to get, I want you to figure out where we're going to put another group of people, and then we'll come back to what that actually means, because it's a little messed up. Okay, so here we have our infinity hotel. We're now full. It's still full. We feel like we should have been over full, but somehow we managed to fit in the same amount of space with one extra person because we can't leave our bellman out in the streets. Okay, so now we have a bigger problem. Brent was hard enough to fit, right? And it involved moving an infinite number of people one room down, which I can only imagine the tips you got on that, Brent. It must have been good. So there's a gap here, and it's an infinite gap. I can't draw it all on my page, but I have something called the infinity bus lines. Okay, and they've just arrived. And it is the football club of all football clubs. There are infinite number of fans of this one particular football team, soccer team, sorry. And they're all on here. They're a bit rowdy, and we need to make space for them, certainly. But they're an infinite number of guests. They're all here. And so I've had them orderly line up. I've lined up quite orderly for you, Brent, so you can figure out who to deal with first. And so we've assigned them numbers. So we've got guest 1, guest 2, guest 3, guest 4. And I'd like it if we could sort them out in order, if possible. And so I need to tell them where to go over my magic loudspeaker. And I need to do it in a way that is just straightforward. Like it took long enough to go through our class and assign numbers. So what I really need to do is say, if you're guest number K, please go to room K plus 1, right? Was easy. We could do that. But I can't assign an infinite number of room numbers. So what can I do that's very organized and that will allow me to fit this many people into our hotel? Oh, and by the way, they have to fit in our hotel, which is already full. What's our end game here? First of all, will they fit? Do we think they'll fit? I mean, essentially, I've got infinity people in my hotel in an infinite number of rooms, and I need to fit another infinity in. A lot of optimists here. Yes, they will fit. Brent, you're going to be busy moving bags. So it's okay if I have a series. Okay, so we can have people move down again. That's a good plan. Now, how many times do I have to do that? So do I just always stick them in room 1? So I did promise a bit of a weird Friday. Brent, I should have warned you. I'm sorry. To bring coffee at bare minimum.
It's all right.
So we could move everyone an infinite number of times. I feel like that could work, except that I cannot do that easily with my loudspeaker. And my voice, as you can tell, is giving out a bit. So to kick someone out, I don't even think someone will be enough. Like, we could kick Kristen out. It was his suggestion. But Kristen, I won't. One, because we need everyone to have a room. And two, I don't think it will solve anything, because that's only frees up space for one. Oh, you're there. Did you leave our hotel? Brent gave you a room number. You're fine. I thought you were in room 312,459. No? That's what it says on my books, at any rate. Okay. If we ask everyone in odd number rooms to move to even number of rooms, all odd number rooms will be empty. I like it. Here's my problem. Remember, we have this prison-like hotel with very small rooms. So I'm not allowed to let you share. So Brent is in room 1. I believe Abhishek is in room 3, right? I'm in room 2. Brent, you're great. But I'm not going to share my room. Daniel. Okay, so now we have another suggestion. So Daniel's suggestion is to take everybody in the room that they're in and ask them to move to their room number times 2, which will leave all the odd number rooms open. What do we think about this? Is that right? Anyone want to vote for that? Give a thumbs up to Daniel if we think that's a solution for this crazy game. Okay, and we see Anik is supporting this. Anybody else want to support? We see a lot of thumbs up on Daniel's comment. Move people to their room. And now this is something I can say over my loudspeaker to all of you who are in my hotel and all the others. Please pack your bags once more. Take a look at your room key. Multiply it by 2 and move to that room. Brent will be there magically waiting to let you in. Okay? So now what we've done is we've taken K and we've moved them to 2K. And now we have the following rooms are free. Room 1, room 3, room 5, room 7, room 9. Perfect. Okay? So now I've got these people on the bus. And so does that, first of all, hold the truck, or the bus in this case. Can we do that? Is there anybody that sort of falls off the edge of the hotel at the end? Does this work for everybody? Some of you have very big numbers. I don't remember who. Schwan, I gave you a very big number back here. You're in 13,789,456,211. How's that going to work out for you? Are you off the edge of our hotel? That's a big number right there. Yeah, well, I've got more than 13 billion. That's just, that's like the first tiny piece of the hallway. Yeah, no, we get much bigger numbers than that. It should be fine, right? I can add 13,789,456,211. I can add those two numbers together and I still get a natural number. I can take any natural number and multiply it and by 2 and get the cleaning staff. You think Brent's expensive. You should hear about the cleaning staff, especially when I have to move them around so much. You are totally right, Shelley. Okay, so all that being said, if that works, then I can fit, yeah, I don't know why they don't solve, this is like population problem. Yeah. Oh, Braden's got the answer. Oh, Schwan, you're sorted. You're apparently in room 2757891242. Brent, I'm sure, has already let you in. Okay, so everybody's room number can be multiplied by 2. It still ends up as a room number that exists in a hotel. So no problem. But what we just did, which is really important to realize, is we've taken our infinite number of guests and we've moved them into what seems like half of our rooms. We're now only in those even numbered rooms. And in fact, what that means is the even numbers. So the rooms, if I say E is all of those X in Z greater than 0, such that X is equal X, let's just say X is even. Fine. Okay. Those are sets that we've worked with before, right? We've talked about these sets. I've never asked you about the cardinality of that set, but I know that I just had an infinite number of people and they fit exactly into that set. And so what we're really saying is that the set of even numbers, which is half of the odd numbers, half of the natural numbers, it's every other natural number, is equal to, it's the same cardinality as the set of natural numbers. There is many even numbers as there are natural numbers. And in fact, what we're hoping is that the set of odd numbers is the same size as the set of even numbers, is the same size as the set of natural numbers, because we have an infinite number of people on a bus that need a room, and we only have the odd numbers to slot them into. Okay, and what I said earlier about how we decide on the size of something, the cardinality, when we were looking at, A, B, C, and we wanted to figure out, is there a way that I can map those elements to counting numbers so that I know how many there are? And I do that by first saying, well, this one is a 1, this one is a 2, this one is a 3. I know the size of the set containing 1, 2, and 3 is the maximum of those numbers. So I know the cardinality of this set is 3. That means that the cardinality, oh my gosh, I love this so much. Sorry, do you see the chat, Brent? It is slightly creepier than I was expecting as well, but I love it. So the size of that set ABC is also 3. That is amazing. I didn't realize you posted. I thought somebody else posted it. Brent. Okay, we are so going to miss you, just for the record. All right. So what we did was we said we've got the even numbers, 2, 4, 6, etc. 1, 2, 3. So here's our natural numbers. So we had our natural numbers, we had our even numbers, and what we did was we found a mapping. And that is the point. We said we're going to take a number and we're going to map it across with a function that says we're going to take x and we're going to move it to 2x. Right? So what you did was you found a way to take the counting numbers and map them to the evens. And in doing so, you showed that the size of our natural numbers set, the set of natural numbers, is the same as the cardinality of the set of even numbers. Okay. So now I've got my infinite bus. I still have to put them into rooms. And Bren's job is never done. So we've got the odd numbers available. How do I move the people on my bus in an orderly fashion? If I have someone on the bus that is in seat B, where do they move to? So here, nice answer. So if you're on seat B in the bus, we're going to have the room move to room 2B minus 1 is the suggestion. Does that work? So 1 is going to go to 2 times 1 minus 1, right? Which is 1. Okay. Seat 2 is going to go to 2 times 2 minus 1, which is 3. So far, so good. 3 is going to go to 2 times 3 minus 1, which is 6 minus 1, or 5, and so on. Okay, so then seat B is going to go to 2B minus 1. I see that, I think, Adam, you fixed yourself, right? Yeah, so the first one goes to room 1, second goes to room 3, third goes to room 5, and you could do a proof if you wished. An exercise left to the reader is that you may prove to yourself that this will work for all values if you wish. But this will work. And so, in fact, we can take those infinite number of people on the bus, escort them into the odd numbered rooms. The even people, we moved everybody. And we moved everybody into the even numbers. I think, Burnley, that's the question. So our first move, so what we did was we had the following situation happen. 1, 2, 3, 4, 5, 6. We started off in this situation, and then we moved such that, 1 went to 2, 2 went to 4, 3 went to 6, 5 went to 8, etc. And then from the bus, we moved people into 1, 3, 5, 7. So they went to 2B minus 1, and these guys went to from K to 2K. Christian, you nailed that. That is so true. Adam gets 45 out of 46 of these questions right, and then he gives him a hard time, gives himself a hard time for that one simple mistake. You guys all track so well. It's amazing. Very quick answers. Okay, so what does that mean then? The set of all odd numbers is equal to the size of the set of all the even numbers, which is equal to the size of the set of the natural numbers. Which might seem a little messed up because, and this is where things are crazy in this realm, and why I bring this up when we talk about sets, because if I were to ask you to draw me, okay, and I'm going to actually ask you to do this. Okay, I'm opening a whiteboard. That you all have access to. Collaborate. Okay, draw me a whiteboard. I mean, draw me a whiteboard. Draw me a Venn diagram, please, of all of the natural numbers. So first, the universe is the natural numbers. Okay, so that's our rectangle. Perfect. And draw me the even numbers and the odd numbers within the set of natural numbers. A Venn diagram. There's no overlap between even and odd, right? I see somebody's got a pen going. You can put an E in your even set and an O, odd in your odd set. O will look like a Venn diagram, and it's in and of itself. Okay, so I see a blue circle. I'm not going to draw. So we see a blue circle. What does that represent for whoever is drawing? Whoa. It's harder to draw in these things than people, realize. Oh, I need to zoom out a bit. Perfect. I can do that. Oh, I see. Yeah, so you can each have your own space and play with it, because you can always zoom out. Okay, so I see the natural numbers, and I've got the even numbers and the odd numbers. Perfect. There's a few going on. There's a heart, which is all of it, I suppose. And what I've seen from all that have been drawn so far, oh. Anna, did you have a suggestion? Oh no, she just muted herself. Okay, so what we see, oh, this is fun. I see there's even numbers, there's odd numbers. Is there anything that overlaps between those if we're just looking at the numbers that are greater than 0? So I see that somebody's drawn a Venn diagram, and if you can't see it, if you zoom out a little bit, we see a few different iterations. So I can't zoom out for you. That's a weird thing. But sorry, Adam, I'm going to erase that little heart for you. I'm not sure that was, I don't know where that was added, but I think that's, I knew it wasn't you. But let's take a look at the one that I've circled in red. This piece is important. Okay, so what we're seeing is, actually, I'll go back to my screen so that we can all see the same thing. It's a bit of a pain that I can't force the zoom in Teams. Okay, so hopefully you can see this now. So I'll show you the few examples that I saw. Okay, so the first one is saying, okay, well, here's the set of the universe. This is our universe, which is the natural numbers, right? And I saw one that I liked that was like this, the evens and the odds. Okay. And you'll note that they're not circles, and that's okay. I think the main point there is that they make up essentially half of it. There's no intersection. Another one that I saw looked like this. It had the natural numbers, and we had the evens and the odds separate. And then over here, I saw another one that looked a bit like this. Odds and evens and the natural numbers. Okay, so of those, now that you kind of think about it in terms of those particular styles, is there any that sort of resonates with you now that you've seen what other people have done? Can you convince us? Okay, so I see the top one. Adam's going with the top one. Remember, he's 45 out of 46, so you can decide to go with him or not. Does anybody want to state, yeah, so 1 or 2 is fine as well, Burnley? Is there any reason that we feel we don't have a vote at the moment for this third one? So if this is 1, 2, and 3, what is it about the third one? Now, technically, the third one's not wrong. I wouldn't have highlighted it if it wasn't. But what can you tell me about the third one that makes you, yeah, Brayden, it's not wrong. But I think the reason people are resonating with some of the others is for a very important reason. He didn't say what was in any of those, right? So what if this is the empty set? I think this is what's getting to people. They don't intersect. So there are no even numbers that are odd numbers, right? And I think we even proved that in one of our assignments. Yeah. So it's okay that we have that there. We just note that there's no numbers that are in both. Now the question I would have, and the reason that I think that people are resonating with this one, what about out here? Because this is the classic sort of Venn diagram. And then you say to yourself, what's out in this space? In the classic Venn diagram. Is there anything out there? Yeah, it's okay to draw it like this, but we have to note that there's nothing out there, the void. That is the empty set. So there's nothing outside of them. And so while we don't typically draw things in this rectangular fashion, this is what's really happening. There is no space outside. But here's what's really messed up. These are not the same. There's no intersection. So this really, there's nothing there. There's nothing out here. And so it really does kind of look like this, right? That they both take up a portion of the space. There's elements in each. And in fact, we know that the size of this is infinity and infinity. The problem is they don't take up all of the natural numbers. There are elements. So if I were to draw these like this, if these are the natural numbers and these are the evens, right? They are a true subset, right? The evens, the set of evens, if I could just call it E, they are a proper subset, meaning they're not equal to the natural numbers. They are a proper subset of the natural numbers. They are all within the natural numbers, if we define them as those even numbers greater than 0, okay? Which is how we've defined our set E. Then this set is a proper subset of the natural numbers. It's not equal to the natural numbers. And it's important to say they're not equal. So if I look at E union N, what do I get? That's just N. That's the natural numbers, right? But if I look at E intersect N, what do I get? There's no real trick to this one. Don't worry. Yeah, E. Okay. So the intersection is everything that's an even number. The union is all of the natural numbers. Importantly, this space right here, this is not empty. This is not the empty set. That is the set of odd numbers. Okay, so why am I saying this? Well, what we said before, what's messed up is that when we have things like this that are not equal, typically what that means is if I was looking, so in the example that I gave where I said, I've got the passwords, we took the size of the outer set, the possible number of 4-digit passwords, and I said, I want only those valid passwords, so anything that doesn't start with 20. And so you said, okay, well, there are 100 of those. So a really valid way to approach that is to say, okay, well, that's just the total set minus the ones that I need to remove. So if I did that with you for this one, that means that if I say, okay, well, what's in here is the set O, and the size of the set O is equal to infinity. And I know, I don't know yet what the size of the natural numbers is, but, the even numbers, but I know that the size of the natural numbers is infinity. And so I know it looks like this. So what I want is to say something like, well, the evens are just the size of the natural numbers minus all of the odd numbers. But what would we get if we did that? Theoretically, we'd get 0, right? We got infinity minus infinity. And here's the tricky bit. None of this really works in transfinite arithmetic. And so it's really important. Yeah. No. So unfortunately, no. These are all the same orders of infinity. And in fact, you can add 1 to infinity and get infinity. And so infinity plus infinity is also infinity, which is super messed up. And so you can't just take infinity, subtract it from infinity, and get 0. It doesn't work like that. Transfinite arithmetic is super bonkers crazy. And in this realm, really 1 plus 1 can equal 1. 1 infinity plus 1 infinity is still infinity. It's a messed up space. And so this is not 0, but in fact, this is still infinity. And I just don't want you to be lured down the road to thinking this always works. Once you're dealing with infinite spaces and infinite sets, things get messed up. Okay? It's a very different space to play in. And now I'd like you to think about for a second, why does infinity matter? Not like in the big fun space, which I would also love to have a chat about, But when it comes to computer programs, why does this concept of infinity even matter? Where do you see infinity when we're, especially in the examples that we've given? How is it that we're going to see infinity come into play? Brent's probably seen it more than his fair share of times while being a student. Created it probably more than a few times, which is not an insult to Brent. It's just a reality of being a programmer. Yeah? Have you ever?
Oh, of course.
I probably did last week. So how do we build infinity into our programs? Quite frequently, I might add. It's too problematic to deal with. Exactly. And it is in this way. One, we don't have a way to kind of create an array that is infinite. But I want you to think to loops. So the reason it becomes problematic is not that it can't deal with it. In fact, here's the problem. Your computer can deal with natural numbers. Easy. Numbers are the thing that your computer lives for. Like integers, piece of cake. But what happens if you ask it to actually deal with all the integers? It takes time. Yeah. We do run out of bits, yeah. But there's a bigger thing. Like say you had a super crazy powerful computer that could deal with all the numbers. We don't even get that far because there's an infinite runtime. Exactly, Stephen. So if I create a loop that never gets to an end, what I'm asking it to do is always keep going, right? I'm asking it to just keep going to the next integer, go to the next one, go to the next one, keep going. Now, it's true, Adam, and I won't get into that, but yes, you'll eventually run out of bits, so you can't actually deal with all of the numbers, but you actually can't for bigger reasons, and that is runtime. So your computer does not have an infinite amount of storage. You don't have an infinite amount of time to wait for, yeah, I would dream of that as well. You don't have an infinite amount of time to wait for your program to run. So there are all of these issues. And in fact, a lot of discrete mathematics, I'm going to suggest, soon, next class, I'm going to write down a note for myself. I'm so excited. There is the most amazing thing that happens every December that all of you in 1105 and 1110 should be doing. It's so much fun, and you have a super leg up because you're in discrete. It's called the Advent of Code, and I love it so much. I really do look forward to it. It's like an advent calendar for programmers. And do not be put off by the fact that you're all just starting out, because actually discrete mathematics is going to help you more than you think. Oh, I wrote that so fast that my computer couldn't keep up. That's sad. Advent of Code. I will write it slower. I won't be so excited. And I will absolutely send you a link. So the way it works is there is a new problem, 2 parts to a problem. It's a competition that's released every day, like an advent calendar through December, from December 1 to December 25. And there are 2 parts to the problem. The first part of the problem takes basic programming that you can do at the end. It's solo, but you could work as a team if you needed to. It's just for fun. And I will absolutely be doing it. So if you ever get stuck, you can always write to me. You can write in any language, because what you're doing is you're solving a problem and then putting in the answer. So much fun. And they're always silly and cute as well. So here's the kick. The first problem is always a programming problem. So you have to write some code to get it to do some fun thing. And it basically never goes beyond 1110. It's really pretty simple. Then there's a second part to the problem. And normally it's asking for something too big for your computer to have time to get there. And so then you have to look at the algorithm by looking at the math, figuring out what's happening, and calculating what the answer is to the problem. And so I know that sounds, man, I should have worked that in. Maybe this will be assignment 9 as a fun one. They are so good. Yeah. Anyway, and if you do get stuck, you should try it out. I'll send a link as we get to December, but it is a blast. Okay, sorry, I digress. But the point is that even there, they've set it up such that you have to understand what's happening beyond just being able to program. So much of what we're talking about and doing is trying to understand how the sets work, how all of the math behind the programming works, so that when you're running something, you can prove to yourself that you're doing the right thing and that it's moving in the right direction. Now I'm over time. Sorry. Anyway, I get super excited about Advent of Code. I'll send everybody the link. And I mentioned I normally have office hours right now. I'll be around throughout the time. You can send me a message on Teams if you have a specific question, but I have a leadership conference that I have to go to. I mentioned on Wednesday, so I will be gone. Hope that was okay for everybody. Hope you don't have any infinity nightmares. Thanks to hear. Also, thanks for that great suggestion early on to get everybody safely to their rooms here. Bye, Abhishek. Sorry to make you move so many times in your rooms. Bye, Adam. Thanks, Adam. Bye, Shelly. Bye, Simran. Bye, Daniel. Sorry, I like to say your names. I really wish I was in a class. I love to see students as they leave and say goodbye. I miss seeing everybody around campus. Soon, we hope. Cross our fingers for a Christmas vaccine. That's what I'm looking forward to. Bye, everyone. Bye, Vishwa. Yes, Burnley. Also, really important thing to be able to do. If you, what you have to do is go out into the main section of chat, and to the right side of it, you kind of right click and it says mute notifications. I know it's a pain otherwise. Yeah. Okay, gotta go. Thanks, Brian. Hope you're not too tired after walking to an infinite number of rooms today.
I need some more coffee.
Don't we all?
Yeah. All right. Have a good one. Talk
Bye.
to you later. Bye.